Good morning, everybody. Please take a seat. Okay. So today we will continue covering the material in the class. In particular, today we will look at how we can, given a model of a certain system, given the knowledge of the input signal, possibly the knowledge of some state at some time t, which could be at some time 0, then we can compute how the system will evolve over time, how the output signal will evolve over time. Okay. Also, during the break, Julian, your TA, brought this little device. This is something that's called a Cubely, right? And one of the exercises, you will actually work with a simplified version of this thing. This is kind of like a device that is kind of like a cube that can actually stabilize itself over one of the corners, turn around, do a lot of other incredible stuff. What do you use this for? I have no idea, but it's just a cool object, okay, cool device. During the break, we will do a demo of this, okay? Before we get started, any questions on the material so far? Okay, so no questions, seems okay. What we will do today is we will look at the, as I said before, how the, given a certain system, given a certain input signal, how we can compute what the output signal will be, okay? So this is what is called the time response of a system. I will cover all the material that you need to know in the slides. If you really are looking for some additional material from a different point of view, to look at things explained in a different way, you can look at the Armstrong and Murray book, this chapter 4 and 5, as well as Goodsella's book, chapter 4, okay? The material is not exactly the same, it's explained in a different way. Of course, the reality is the same, right? Okay, the subject matter is the same. So don't, for me, the point of looking at these books is just to have an additional point of view, maybe have things explained in a different way if you want to have them explained a different way, okay? So we are at this point, so still on track. Today what you should be able to do is really understand this basic concept. So the way that we deal with computing the response or analyzing linear systems is really a basic idea, that of divide and conquer. If you remember the definition of what a linear system is, what you will see is that the key property of a linear system is that what is called also the superposition principle, okay? So instead of trying to compute what would be the output to some very complicated input, what you can do is break down that input into simpler components, okay? For each of which you know how to compute the output, and then reconstruct the output by adding all of these elementary output to elementary pieces of the input, okay? Divide and conquer, again. So we will understand how to do that. We will do that first on a first-order system, so that everything is very simple math, something that you can follow with the things that you already know from your analysis courses, your differential equation courses. But then we will move to the higher dimensional case, okay? So in this case, we can no longer keep working with scalars, okay, with numbers. We'll have to work with matrices. And in particular, we will need to learn what a matrix exponential is, okay? So this will be the next step. And then we will use this matrix exponential to compute the response of a higher dimensional, higher order linear system, okay? As we wrap up the lecture, what we'll do is we will look at several definitions of the concept of stability, and then we will look at ways by which you can check whether or not a system is stable just by looking at the matrix A and its eigenvalues. Okay? let's get started. So to explain this time response, what we will do is we look at probably one of the simplest examples that you can imagine. Okay, it's a temperature control kind of example. So it's deep winter, it's cold outside. You are returning to your cabin in the mountains. Okay, so the temperature outside is 0 degrees. Now, since you didn't want your water in the pipes or whatever to freeze, before going out this morning, you set the heater to some low value, right? So you don't want to waste energy, but at the same time, you don't want the water in your pipes to freeze, okay? So you set it to power 1, just the lowest setting on your heater, okay? You go out, ski the whole day, do whatever you like to do in the mountains, come back to the cabin, and then, as you would expect, the temperature is actually quite cold, right? It's above freezing, because there was the point in leaving the heater on. But what you notice is that as you come in, the temperature is actually 3 degrees, okay? So it's too cold for you, so then what you do is you switch the heater on to full power, let's say power 5, okay? Now, what I would like to understand is how does the temperature in the cabin evolve over time, okay? So time 0 is when I come back home, okay? So in the past, the heater was set to 1, okay? And what I know is that when I open the door, the temperature was 3 degrees. And now, from now on, I set the power to 5, and I would like to understand what will happen to the temperature. What do you think will happen? Have you ever done that? Ever stepped into a cold house and switched on the heater? What happens? Okay, very good. Right, so your expectation is that something like, can I choose? Okay. So your expectation is that, the temperature will start from here, right? And then will start rising first with a steep incline, right? But then will kind of level off, right? Does that match your expectations? Okay, well, probably this would not come to a surprise to any of you, right? So we kind of know in our guts, intuitively what will happen. Now what we will try to do is try to see how you actually can compute that mathematically, okay? So yeah, the end figure will not look very much different from this one that I just drew, okay? But now what we want to do is understand how you can actually compute that. Okay, so in order to do some math, we need some model, and what I'm telling you is that, we assume that we know that a good model for the temperature dynamics inside this cabin is this one that they give in this, in these equations, okay? Remember that we write the model of a linear time invariant system as x dot is equal to ax plus bu, and y is equal to cx plus du. In this case, a is just the scalar -2, b is the scalar 6, c is the scalar 1, right? And d is the scalar 0, okay? Talking about units, we measure the temperature in, say, degrees. U is the power setting on the heater, it's dimensionless, and we measure time in hours so that we get, like reasonable numbers here, okay? Good. Okay, so now let's get back to the theory. So now what we want to do is we are given an input signal U, okay? So this is an input signal that, oh yeah, question? Yep.
How do you arrive at these scalar values?
Just somebody gives you this model, okay? Yeah, this is not the subject of this course, okay? So, there is another course on system modeling and things like that. Or, when you did you take any courses on, thermodynamics or, any kind of like heat transfer or things like that? This is really where you get something like that, okay? In this course, it's more about, given a model, how to control that dynamical system. It's not how you get the model, okay? On the other hand, you get something like that, right? So this is how fast the temperature changes. And of course, the more heat you put into the system, the faster the temperature will change. Of course, you're also losing temperature to you're losing heat to the outside, right? Because outside is colder, right? Outside, the temperature outside is 0 degrees. So every time your temperature is above 0, then you're losing heat, right? Every time your temperature is below 0, you're actually gaining heat, okay? So that's why you have this negative sign and multiplying your temperature x, okay? Sure. Okay, so now we are given u, we want to compute the output y, okay? Remember that, as I said before, the definition of a linear system is one where, given any two input signals, okay, I can compute the output to the linear combination of the input signals as the linear combination of the outputs that I would have generated just applying those simple elementary signals UA and UB, okay? And this is the #1 key point in everything that you do with linear systems, okay? Because if this superposition effect applies, then you can take any complicated problem, split it into little pieces that you can know how to solve, and construct your solution to the complicated problems by summing the solution to the easy problems, okay? Divide and conquer, okay? So this is exactly what we will do. In particular, what we can do is we can choose to split the input signal into everything that happened in the past plus everything that happened in the future, okay? So essentially what I'm doing is I am splitting the signal into, this would be the past signal, sorry, okay? So this would be U in the past, okay? So essentially I use whatever I gave to the system in the past, and then I set it to 0 from the present onwards, right? And then I will have the other signal, which is the future, okay? Which would be something like that, okay? And you can understand that if I add my past signal to the future signal, I will get the actual signal over all of time, okay? Now, something else that we know, because of the system is causal, right? So physical system is causal. Actually, we can summarize the effect of everything that I did in the past just through the knowledge of what is this state of the system in the present, right? So as I walk into the door and I feel that the temperature is 3 degrees, do I really need to know whether the heater setting has been 1 for the entire past of for the entire history? Does it matter that maybe I had a little gremlin in the house that was switching the heater on and off, right? But does it really matter, right? So as long as the temperature, as I set foot in the house is 3 degrees, that's all I need to know. Okay, is this concept clear? Knowledge of the state at this point in time, right? 3 degrees. That's all I need to know about the past, okay? In order to predict the future, okay? Questions? Okay, so in a sense, what I can say now is that I can, do my divide and conquer. I can compute my output by looking at what is the response, what happens to my system if I only turn on the heater in the past, plus whatever happens to my system if I only turn on the heater in the future, okay? Now, the part where I look at what happens if I only turn on the heater in the past and then set it to 0, that is exactly the same as walking into the door, knowing that the temperature is 3 degrees, I do not switch on the heater, what happens in that case, okay? So this is something that we call the initial conditions response, okay? So this is looking at what happens to the temperature in the cabin if I open the door, feel the temperature, switch off the heater. What do you think will happen in that case? Well, we will look at that in a second, right? So anyway, we can split the problem into these two pieces. Look what happens when I have this initial condition, okay? Then what I will do is, now let's assume that as I walk into the door, actually the heater was set to 0 for all the past history, right? And then now I turn it to up to 5, okay? So my initial condition will be 0, but now my input will be equal to the input in the future, okay? So we will compute these two components of the response separately. We will start with the initial condition response. This is also called the homogeneous response. And then we will look at the forced response, okay? Okay, so then what we will do is, once we have the homogeneous solution, the homogeneous response, and we have the forced response, what I will do is I will just add them up, and then what I will get is the actual response of my system. Okay? Now let's go back to your intuition. So what do you think will be the response, the initial condition response? Okay, so now I start here. The temperature is 3 degrees. Okay, and I do not turn on the heater. Okay, I actually switch it off. What do you think will happen to the temperature? Yeah, it will go down, right? And will go to the outside temperature, okay, to match the outside temperature. At that point, we'll be at an equilibrium, okay? Conversely, what do you think will happen if I walk into the door, the heater has been off for the, from the beginning of time, okay? So the temperature will be 0, okay? And now I turn on the heater. What do you think will happen in that case? Well, now, same thing as before, with the only difference that I'm starting from a temperature of 0 degrees, right? So let's look at how you can actually compute these two curves. The initial condition response is also called the homogeneous response. We have to solve this initial condition problem, right? So we have an ODE with an initial condition. The ODE is x dot is equal to AX. You see that what you have here is only terms that contain x or its derivatives. That's why it's called homogeneous, okay? So there is no term that involves the input, okay? So x dot is equal to AX, x at time 0 is equal to 0 to x naught. This is the initial condition, okay? And y is given by Cx of t, okay? What is the solution to this differential equation? You should have done this in analysis or some differential equation course, right? So you should know that the solution of this ODE is just e to the power at that multiplies x naught. You can check that this is actually a solution because now if you substitute e to the power at times x naught in here, what you get is actually an inequality, right? What is the derivative of this function? The derivative of this is a times e to the power at x naught, right? But then on the right-hand side, what you will have is a times e to the power at x naught. So you have an identity on both sides, okay? So you can check that this is actually a solution, okay? Now, as you can see, the way I wrote this formula is e to the power at, I put it on the left. You will understand why in a bit. Anyway, I put it on the left, and this is something that multiplies my initial condition x naught, okay? So you can also think of this as some function phi of t that multiplies my initial condition. This function phi, which in this particular case takes the form e to the power at, is also called something that is called the state transition function. Why is it called the state transition function? Because it's something that multiplied to the initial condition, to the initial state, gives you the state at time t. Okay, I'm losing people here. Questions? A second to digest this stuff. Yep.
This slide where you explained how you split the signal.
Yeah.
The past and the future.
Yeah.
I don't exactly comprehend what the benefit of doing that is.
Okay, so remember that since we have a causal system, right, we know that my initial condition, my initial state, right, so essentially the summary of everything that has happened in the past can be given as this state at time 0, okay? So now, as you notice here, what I'm doing, I'm not solving a differential equation with a forcing input. I'm solving a differential equation with an initial condition, okay? So here I'm solving just the homogeneous part of a ODE problem, okay? That's something that, doesn't matter how complicated the input was in the past, it's just an initial condition. Okay, you see the simplification? As I said, I said before, I could have had a little monster who went in my cabin and was changing the heater setting all the time, okay? But it doesn't matter to me because I know that when I entered the house, the temperature was 3 degrees. That's all I need to know in order to predict the future, okay?
So this is splitting up, that's the initial condition.
Right, so essentially I'm splitting up the past, i.e. that is the initial condition, and then I will compute what the response will be to the future input, assuming 0 initial condition.
Why do you assume 0?
Oh, because then I make my calculations easier, right? Okay? Because I know that if the initial condition is 0 and I don't apply any input, the state will always remain 0. Okay? So just a way of simplifying the calculations. Okay? So first, but you remember, so when you did, ODEs, right, when you solve differential equations, what you may remember in the case of linear differential equation is that you can compute the solution by adding the homogeneous solution, right, and then, I don't know how you call it, is a particular solution or is a forced solution, right? That is something that depends on the right-hand side in the ODE. Right? This is exactly what we are doing. Okay, we are splitting these 2 pieces. Okay. Okay, so this is the solution of the ODE. Right, and in particular, in this case, what we know is that, well, okay, so the output will be C times the state, right? So in particular, it will be C times e to the power AT times X naught, okay? In our case, what would this be? We know that X naught is 3 degrees. We know that A is -2. So C is 1. So what I know is that Y of t will be given by 3 times e to the power -2t. Okay? So how do we draw this? What is the value of Y of t when t is equal to 0? E to the power 0 is 1. Right? So we know that y at time 0 will be equal to 3. Is it surprising? No, because that's what we know that we experience as we enter the house. Now, as one of your colleagues said before, initially the temperature will actually decrease more steeply, right? How fast does your temperature decrease at time 0? Actually, if you compute the derivative of this function, what you get is that, look, so here what I have, the coefficient that multiplies t is at 2, okay? So this will be equal to 1 when t is equal to 1/2, okay? So, and in particular, this is one way that you can construct this curve because you know that if you take the tangent to the curve here at initial condition will intersect this axis at at t is equal to 1/2, okay? And the actual shape of this response will be something like that, okay? So we'll be tangent to that line at time equals 0, and then it's an exponential that decays and goes eventually to 0, okay? This time here is actually called the time constant of the system, okay? This gives you an idea. The shorter the time constant, the faster the response will be. The longer the time constant, the slower the response will be, okay? Okay, the time constant tau is actually given by -1/a, okay? In this case, a is equal to 2, so this is actually equal to 1/2, okay? Questions? Does this surprise you? Shouldn't, right? Okay, quite. If you have questions, ask. Otherwise, please. This one? This is a tau. Sorry, this is an A. Okay. In this case, A is -2, right? Okay? So this is what happens if I just step into my cabin and the heater is off, okay? Now, okay, so this is some scary math, okay? But it's actually not that terrible. So this is to understand how you compute the force response, okay? So now what we have is you need to solve this ODE, okay? So now we had to solve x dot of t is equal to a xt plus bu of t with initial condition 0, okay? So we took care of the initial condition before, now we are setting the initial condition to 0. How do we compute this thing? Let's not go through the math, okay? You can go through the math on your own. You don't really have to. You know, it's informative if you do. Essentially, you just integrate by part some ODE, okay, some integral. But at the end of the day, the important thing is that what you get is this. My particular solution of this ODE is given by x of t is equal to the integral between 0 and t of this horrible stuff inside this horrible expression, okay? Now, this horrible expression is something that is called a convolution integral. You can think of it, look at it this way. This is kind of looking at what is the effect of an input given at time tau after time t minus tau has elapsed, okay? And you do this for all possible taus so that you get the total response, okay? I'm not asking you to understand this formula, take it for granted. The nice thing is that you will actually not have to compute this integral ever, okay? You will not have to compute this integral ever by hand, only we do it in some examples in class, okay? As you may notice, this is e to the power a t minus tau. This has the same form of the e to the power at that we looked at before. That's the state transition function. So you can also write this integral as the state transition function computed over a time difference of time t minus tau times the input at time tau, okay? Convolution integral, important thing when you do these kind of calculations. It's good to know for the proofs and for the analysis part. You will in reality not have to compute it very often in practice. Now, what form does it take in our example? Well, this would be if you just do the pattern matching and you just rewrite the formulas. In this case, what you get is you have the y will be given by 30 times this integral e to the power minus 2 that multiplies t minus tau d tau. You want to compute that integral? I will not do that. So I have the steps here on the slide. You can do it on your own. But what you get at the end is this expression here, okay? So this is actually the solution of that integral. What you see here is that this is something that you can write as 15 minus 15 that multiplies this decaying exponential. So what does this function look like? When t is equal to 0, what is the value of this function? When t is equal to 0. When t is equal to 0, e to the power minus 2t is what? Is 1, right? So 1 minus 1 is 0, right? So I see how you got to there, right? But so the initial value of this response will be 0, right? When t is very large, what will be y? When t is very large, e to the power minus 2t is what?
0.
This will be 0, right? So eventually my function will go to 15, okay? So if this is 15, okay? So I know that eventually my function will go to 15, okay? How quickly does it go to 15? Notice that the exponential is still minus 2t, so the time constant will still be 1/2, okay? So it'll still be the case that by the time that I get to 1/2, essentially this will be the tangent, okay? And my function will be something like that, okay? We'll eventually go to 15 degrees, that's my steady state condition. And initially will rise more steeply, and in particular, the tangent will be given by the straight line that intersects the steady state value at the point given by the time constant, which is 1/2. Okay? Yep, question? No, you were just, okay. Other questions? Does it make sense to you? The shape of the curve should make sense, right? So you step into the cabin, temperature is 0, switch the heater on, what do you think will happen? Okay, why the buzz? What is? Questions? What isn't clear? Speak up. I mean, I don't know, right? So if you don't tell me if there is anything that is not clear, I don't know. Okay, anybody who doesn't believe this? Yeah. No, okay, so remember, divide and conquer. So we looked at the effect of the initial condition before, okay? Now we're looking at the forced response. The forced response is assuming that the initial condition was 0, okay? And then look at what happens if I turn on the heater. The next step is to put these things together, right? So now what we do is we put these things together, and then what we have is, this guy here, this was the initial condition response, plus this guy here, this is the forced response.
Could you explain again how you got, like, if you go one
yeah.
back? Well,
how I got this formula?
What do I have to do with that, the last, formula? I don't understand.
What you had to do, or how I got to that formula?
Both.
Both? Okay, how I got to it is, if you remember, you go back to your days in which you were taking analysis, right, computing integrals, solving differential equations, right? Go back to those painful days, okay? I don't know how painful they were, but usually they are. Right? It's okay. So how do you integrate this equation? One way of integrating that equation is, so I had to integrate this equation here, okay? One way of doing that, I'm telling you, okay? So you can figure out different ways, okay? It's not the only way. One way of doing that is multiply both sides by e to the power minus a tau on the left and on the right, and then integrate between 0 and t. Okay? Now, as you can understand, what I have on the left-hand side is e to the power minus a tau times x dot of tau d tau. I know that x dot d tau is essentially dx tau, right? So then what I can do is I can integrate by parts, this part, the stuff here, and then what I get is this expression. Okay, so this is the integral by part of this. Okay, now what you see is that this integral is the same as this part of the integral. So this thing cancels with this one. Okay, and then what you're left with is, okay, so you still have this e to the power minus at that you had to move to the right-hand side. Okay, and then what you get is, at the end of the day, you get this formula. Okay, now you see this formula is actually a function of t, right? Because you do have tau in the integrand, right? But you're computing the integral in d tau. So tau will eventually disappear, and the right-hand side is actually a function of t. So this is will be just a function, okay? Essentially, this is something that describes how the temperature will change starting from initial condition 0 as I apply my future input. Okay? And doing the calculations, in the case of the cabin, this is what you get. Okay? In particular is this curve here. Okay? Putting things together, as I said, what you have here is the initial condition response. Okay? So this is the initial condition, and this is the force response. Sorry, it's kind of hard to write on the glass here, so that's why. My handwriting is terrible, and it's even worse when I write on this thing. Okay? So you see how I constructed this solution, okay? So this is my state, and then I know that I can construct my output just by multiplying the state by c, okay? So just I do the same thing and just multiply by c, okay? Now, something that you notice or you may notice is the following, that the response actually will be a linear combination of terms that are not arbitrary, okay? This will be a combination of terms that contain e to the power at, right? If you remember, that is the function that describes how the system will evolve on its own if I apply 0 inputs, okay? So this is the system natural dynamics, okay? If I start the temperature for some reason at 3 degrees and I do not switch on the heater, the temperature will decay as this exponential, okay? So this is natural dynamics. Then if you look at what the solution of this integral looks like, what it will have is, will contain again terms that are of this form, e to the power at, plus terms that actually take the shape of the input and possibly its derivatives. Okay, you can check that, at home. Okay, but this is, for your knowledge in general. Okay, so going back to the cabin, what we know is that the solution, the initial condition response was something like that. The force response was something like that. What do you think will be the sum of these two? I'm adding, so here I'm adding 3 plus 0, so it will be 3, right? Eventually, it will be 15 plus 0, so it will be 15, right? In the meantime, it will be something like that, okay? So now we go back, so when you're asking, why doesn't the temperature start from 3? Yeah, it starts from 3 when you take into account the initial condition response, okay? You see what, how we did this thing, what we call this divide and conquer. So essentially we computed these two components of the response separately. Yeah, you could have done it at the same time, right? If you give it to Mathematica, Mathematica will solve it, right, in one step. On the other hand, we are human beings, and we typically, when we do calculations, we typically like to do calculations by small pieces, right? And so this is how we separated these pieces, okay? Questions? Oh no, there was just Julian. I saw recent. Okay. So far, so good. Okay, so now we kind of cheated because A was just a scalar, right? So when I computed e to the power A, that's an exponential that you know how to do, how to compute, right? And everything that we have done so far is something that you have already done when taking the analysis classes, okay? Now, it is a little bit unfortunate that in most systems of interest are not first order. You know, the state is not just one scalar. In general, your state will be a vector of dimension n, okay? In which case, your matrix A will not be a scalar, will not be a 1-by-1 matrix, but will be an n-by-n matrix, okay? So can you do exactly the same thing that we did up to this point? Well, not really, or not until we are able to write something that is e to the power a matrix. What does it mean to take the exponential of a matrix? Okay, and this is exactly what we are going to do next. Okay, so you know, the nice thing about everything that we have done so far is that actually the main principles hold, and you will see that at the end the solution will look formally the same as the solution that we have computed so far. Unfortunately, you had to deal with matrices. Okay? Questions? Is this clear? You know, roughly. You know how? You know the exact shape of the formulas. That's something that you can do on a piece of paper on your own, and you know convince yourself that is actually a solution. The key point that I wanted to, the key message here is that the way that you compute the solution is actually by separating what happens if you have a non-zero initial condition and zero input, and what happens when you have a zero initial condition and a non-zero input. Okay? You compute these two in different ways, and then you put them together. Okay? This is really the key message. Okay? Good. So now we know how to do to compute the response of a first order system, right? When the matrix A is actually a scalar. Okay, it's a 1-by-1 matrix. Okay. What we found is that the initial condition response was determined by this exponential, e to the power at times x naught. Okay. Now the question is, what happens when A is a 2-by-2 matrix or a bigger matrix? Okay. Now, if you realize that the key property of the exponential was the fact that if we substitute x of t is equal to e to the power at, what we have is that the derivative of this function is actually equal to a times that function, right? So that really tells me that the exponential is the solution to x dot is equal to ax, right? Okay, so what is the function such that its derivative is a time the same function? The exponential. Okay, so this is really the key property of the exponential that allows us to say that this is actually the solution. Now, something that you may or may not remember is the series expansion for the exponential, right? So you may remember, I mean, you've seen this, okay? I'm sure that you've seen this, but you can actually write the exponential as the sum of this Taylor series that is given by 1 plus at plus 1/2 at squared plus ... 1 over n factorial times at to the power n, okay? So this is the Taylor series expansion of the exponential, right? You seen this already? Probably yes, okay? Good, okay, so what happens in the matrix case? What we would really like to happen is the following. We would really like to write this e to the power at, whatever that means. Okay, so but now this is a matrix, right? Okay, let's keep going after the break. During the break, Julian will show you a demo with this cubelet, okay?
Also, hört man mich? Vielleicht geht ein bisschen auseinander. All right. Maybe give it a bit of space. Then the camera can also see the cubely. Okay. There we go. Let's do it like this. So one of the really interesting parts of control theory is actually seeing it come to life. And that's why I brought the cubely. Okay, so didn't start up perfectly just now, but it learns, so it should eventually work, yes. And it can actually spin up. The interesting thing is that it has 3 wheels. And we're going to look at a, can you, you may see, I think someone is in the camera.
This one and project it.
This one?
Yes.
Do you think that could work? I think it's easier if you all sit down a little bit, and either you can see it up there in the screen or directly here. Okay. So as I was saying earlier, there are 3 wheels in this cubely, and it's kind of meant as a motivational example of why I personally think control theory is very, very interesting. When you actually get into the math and so on, this is one of the things that you can eventually do. So this cubely is a multiple input, multiple output system. It has 3 wheels that are actuated. And this is actually a very similar way that also satellites are controlled. So if you're using your cell phone, then the satellites that you may use actually have to be oriented towards Earth, because otherwise, of course, the signal wouldn't get to us. And the way that satellites, among other ways, can orient themselves is also using these kind of spin wheels that when you turn a wheel, of course, the wheel turns you in the opposite direction. Usually we don't feel it because we stand on the ground and there's a lot of friction involved. But in the case of a cubely, and also in the case of satellites, can actually be used. So the cubely actually has 3 ways of operating. You can see here. That was a bit too strong. Okay. Sure. It always takes some time to start up again. Okay, let's put it down. So there's 3 ways of operating. One is just balancing on the edge. One is operating on, it goes from the edge to the corner. So now that's what it's supposed to do. When it does it the first time, it could happen that it doesn't actually get it right, but then it learns. So there's also a learning part involved in this design. And then it gets it right. I mean, so far as I've seen, every time. So now it, I think someone reset it, and it actually has to learn to get there again. It's gotten closer, as you saw. And slowly but slowly, it's getting there. There are also other really interesting demos of learning with robotics that were done with quadcopters in Professor D'Andrea's group. And now, as you can see, is actually operating on the corner, which is very nice. And the crazy thing, which unfortunately not everyone will be able to touch it now, is that you can actually press it, and you feel the force acting against your finger. So it's actually giving you a force back. Of course, you can't push infinitely long because the wheels can only get this fast, but it's very interesting to feel the force. I mean, I can't slam it, obviously, just like you can't be, I don't know, hit by a bus and still stand on your feet. But the principle still holds. So let's try the third mode, which I think is the most spectacular one. And again, it might not work on the first try, so bear with me. But what it's trying to do is to jump directly onto the edge. And I was actually quite amazed when I first saw this, because I thought, okay, from the corner, of course, it can get onto the edge, onto the corner. From the edge, of course, it cannot get onto the corner. But, that's the presentation effect. I'll just give it some time. It's getting closer. So probably next time it'll get there. No. It really works. I think when you do press it for a while, then it resets the learning, and it actually has to start off again. See? So this is actually something that I think is really exciting, that was also developed here at ETH, at IDSC. And that's, I think, meant for you as an example to see what interesting and I think beautiful things we'll eventually be able to do with this kind of mathematics that might, at least for some, seem dry at first. All right. Do you have any questions? Maybe. Please.
How come that it has to learn instead of just actually having a number which works corner?
Right. I mean, this is something that will come up also in our exercises or in your experiments with the seesaw, and that is we do model things because we do know things about the world, these systems, but very specific things. I don't know, the way the ground works, or maybe today it's colder than in the laboratory. And there are small changes that occur that are not like our model is, or maybe there are even big changes that we did not anticipate that are not like our model. And frequently what we do to overcome these differences is learning, or something called system identification, which you can learn more about, I think, usually in the masters. And this is why the Cubely also learns, because getting it just right is difficult, because you don't really, I mean, there's no way to easily know the exact amount of force, because getting it, you kind of have to get it just right, because, yeah. Good question, thank you.
You have to get it exactly right once it gets close to this equilibrium point.
How does it know it? That it's closer?
What's annoyed? Is yours on?
Mine is on. Okay. I don't know exactly how this thing works, right? But what you can imagine is that, this is measuring things like the acceleration, right? And is actually measuring the direction of where gravity is. And of course, what you want to do is, get gravity to be aligned with, that particular diagonal of the cube, right? And also you measure angular rates, angular velocities, and you want to bring them to 0, right? And so when you see that, we'll see, right? So essentially when you see that your Cubely is leaning to one side, right? So then gravity now is pointing in another direction, and you have an angular velocity in some direction, then you want to counterbalance that, right? So this is what it's doing. But typically you can do this by feedback when you're sufficiently close to the equilibrium point. It's hard to do that by linear feedback when you are starting from far away, right? So when you're starting from being flat and you want to get on the point. right? So that's why in that case probably there was some learning that was necessary. Okay.
All right.
Thank you.
Thank you.
As Morris coming.
Ich meine nur auf der Seite.
Okay, ist das like the sensor?
Ich glaube, hier
Okay.
Aber ich meine, hat das 3 Wheels, also könnte er auf dieser Seite starten?
Okay. Okay, let's get started again. We have more opportunity to ask questions at the end, okay? So, okay, let's resume from where we left. Okay, so what we would really like to do is to be able to write this matrix exponential. At this point, this is just an invention, right? So let's define this exponential of a matrix. I have no idea what it is, but wouldn't it be nice that the same property holds that it used to hold for the scalar exponential? Okay? And in particular, the property that I would like is that if I take the derivative of this function, yeah. Thank you. Okay. Thank you. Very good point. So again, what I would really like to have is that if I take the derivative of this exponential, what I get is a times that exponential. Okay? So this is a matrix. This will also be a matrix. I really like it to be true also if I invert the order of those two matrices. Okay? Now, remember how remember the Taylor series expansion of the scalar exponential. So what I will do, I will define my matrix exponential as the sum of something that looks very much like the Taylor series expansion of the scalar exponential. So what I would say is that, okay, so e to the power at, where a is a matrix, will be given, so notice that this is identity. This is not the number 1. This is the identity matrix, which in the scalar case is the number 1, okay? But otherwise, it's just a matrix with only 1s on the diagonals and all 0s, okay? So we write this as identity plus at, where now a is a matrix, times the scalar t, plus 1/2 at squared plus ... plus 1 over n factorial at to the power n. Formally, this is exactly the same thing as the Taylor series expansion of the scalar exponential, but now this thing is applied to a matrix. Okay? Now, what you may want to check is that if you compute the derivative of this guy here, what would be the derivative of the identity matrix? It's just the 0 matrix, right? The derivative of constant is 0. What would be the derivative of a that multiplies t? That would be just would be just a, okay? So on and so forth, right? So you can actually check that if you take the derivative of all of these things, then you satisfy this property. Amazing, okay? But this is exactly what allows us to use, now we can say that in the general case, even when A is a matrix, we can write that x of t will be given by e to the power at times x naught. Okay? Now you can see why I chose to write these factors in this order, because now e to the power at is a matrix, and by n matrix, x naught will be a n-dimensional column vector, okay? So can I write x naught times e to the power at? No, right? So I had to write these two factors in this order, okay? So I can write my solution, my state solution will be, my state will be given by this e to the power at times x naught. And now I have this state transition function, which is a matrix function that would be the matrix e to the power at. Okay? So essentially what we have learned here is that as long as we define the matrix exponential in this way, as the sum of this series, then everything that we wrote for the scalar case will still hold when I substitute a matrix A for the scalar A. Okay? The equations look exactly identical. There is only the difference that now the argument of that exponential is actually a matrix, is no longer a scalar. Okay? Just kind of like an important difference, but in terms of how you write the formulas, it doesn't matter. Okay? So we can just redo all the calculations that we've done before, the same argument, split the initial condition response, the forced response, and what we get is, again, x of t will be given by the initial condition response plus the forced response. Okay? The only difference is that now this is a matrix exponential. These are all, this is a matrix exponential, these are all matrices. Okay? So formally, the equations are exactly the same. Okay? So the only thing that you should keep in mind is that, in general, matrices do not commute. So you had to maintain the order of things. Okay? When these are all scalars, you can just commute the factors in a product. In the case of matrices, you, in general, cannot commute the factors. Okay? Just a fact of life, fact of math, algebra. Okay, so how do we actually compute the matrix exponential? First method is through the definition. So arm yourself with a lot of patience and a lot of paper and, and just compute all those terms, right? Identity, compute A squared, multiplied by A, you get A. Okay. Multiplied again by A, you get A cubed, A to the 4th power, to the 5th power. After a few centuries, you'll converge to something. So that's not something that you really want to do by hand. The shortcut is go to MATLAB, and there is a command in MATLAB that computes the matrix exponential for you numerically. Now, notice that if you want to compute the exponential of a matrix, then you have to use the command xm, the little m at the end here, okay? And that will compute the exponential of the matrix A times t. I'm saying that because I guarantee you that you will get this wrong at some point in your career, one or more times. I did it several times. So what you do is you just write exp A, and now, unbeknownst to you, what you're getting is not the matrix exponential, you're getting the matrix which contains all the elements, the exponentials of the elements of the matrix, which is a very different thing, okay? Pay attention. I guarantee you that you will get it wrong at some point, but make an effort, okay? Try to remember to put this M. Now, our little secret will be that even though now we will go through some mechanism of how you can actually compute this exponential of a matrix, the little secret, don't tell anybody, is that actually you will never have to compute it by hand. Except possibly for some of the exercise sessions. Maybe some exams, but those are details that don't matter. Okay, so in principle, you can compute it by hand in these ways. A much better method to computing the matrix exponential is actually, if you really want to do it by hand, is not to do it with any of these ways. And by the way, this is the way that MATLAB does not compute the Taylor series expansion. What MATLAB does is finds a transformation of the matrix. We will see more how you actually do it next time. But you can find the transformation of the matrix or another choice of coordinates, another choice of state, such that the matrix A is diagonal, right? Why do you want to do that? If you can find a choice of the state, a choice of coordinates, such that your matrix A is diagonal, then the matrix exponential of this matrix is actually given by the exponentials of the entries. Okay, so this will just be given by the diagonal matrix which contains on each term on the diagonal just exponential of that particular entry. Okay? You can check that this will be the case, right? So when A is diagonal, what is A squared? It's just a diagonal matrix with the square of the elements, right? So you can understand that when A is diagonal, when you compute the Taylor series expansion, what you have is a diagonal matrix which contains in each element the Taylor series expansion of that particular element. Okay? So then you converge to this thing here. Again, it's an unfortunate fact, that would be nice. It's a little bit unfortunate fact of reality that not all matrices can be converted to diagonal form. Sometimes you will have to be, to satisfy yourself with something that is called like a Jordan form, okay? And this is a form where what you have is, equal elements on the diagonal, and then you have this pesky one in the corner, okay? Or in the above the diagonal in general, okay? Now, the nice thing is that you again can compute what is the exponential of this Jordan 4 matrix, and what you get is another matrix that looks, is upper triangular. On the diagonal, you have the exponentials of these terms. And then what you have is on the, above the diagonal, you have an entry that actually contains time multiplied the exponential, okay? We will, we'll find out how to compute the transformation next time. If not, we'll do it today. For now, let's just work on diagonal systems and, somewhat on Jordan form systems, okay? Now, if you remember, you may have done something like this already, looked at similarity transformations and things like that in linear algebra, if you're taking any linear algebra class, or you're taking any linear algebra content. You may recognize that the terms that appear on the diagonal, both in this case and on this case, are actually the eigenvalues of the matrix A. Okay? Good. Let's move forward. Okay, so what is the simple case? The simple case is one in which we have the matrix A can be written as a diagonal matrix, okay? And the entries on this diagonal are real numbers, and they're distinct, okay? Or they can actually be equal, but as long as you can diagonalize this function, okay? Now, if you do calculations, we are computing the output, so we are multiplying by some row vector C and by some column vector X naught, that is the initial condition. So at the end of the day, what you get is a scalar that is given by a linear combination of the exponential of lambda 1, that is the first eigenvalue, times some constant that multiplies the exponential of the second eigenvalue, okay? So in general, what will happen is that your solution will be given by something that multiplies some exponential plus something that multiplies another exponential. You add the two, what you get is something like that, right? So the black curve is not quite an exponential, but is given by the sum of two exponentials, right? In particular, you may notice that in this case, what I have is a first exponential with a very short time constant, right? So you see that it's an exponential that decays quickly, right? And then I have an exponential with a longer time constant, that is an exponential that decays more slowly. And the black curve, you see that's something that initially decays quickly and then slows down and eventually goes to 0, okay? So this is something that you will see often, right? So this is the case where you have real eigenvalues, okay? And typically, and the response to when your system has real eigenvalues is a response that is given by the sum of a number of simple exponentials, okay? Maybe with different time constants. Okay, and this is where the panic starts. Okay. Now, again, another unfortunate fact is that very often you have a perfectly decent matrix with real entries. You go compute the eigenvalues, and what you get is complex eigenvalues. What the heck is that? Okay? Now, the saving grace here is that typically, whenever you have a real matrix and you compute the eigenvalues will be either real or complex conjugate. Okay? So it may be the case that you will get when you diagonalize this matrix, what you will get is on the diagonal, on the diagonal, what you will get is two complex conjugate numbers. Okay? Let's call them, let's call sigma is the real part of these numbers, and omega is the imaginary part. Since I know that these two numbers, these two eigenvalues, need to be complex conjugate, then I know that one of these entries will be sigma plus j omega. J is the imaginary unit. J is the square root of -1, right? Okay. So one entry will be sigma plus j omega. The other entry will be the complex conjugate, will be meaning that will be sigma minus j omega. Okay? Let's pretend that these are normal, decent, real numbers, right? So in that case, what you will do is you will compute the solution as something that multiplies the exponential e to the power sigma plus j omega t, right? Whenever I have the sum of exponential is also the product of exponential, right? So sorry, whenever I have the exponential of the sum of two terms, I can split it into the product of two exponentials, right? So I can write exp of sigma t times exp j omega t, okay? And then on the other side, what I have is some other coefficient that multiplies exp sigma t times exp minus j omega t, okay? Now, I'm just doing calculations. I'm just oblivious to the fact that these are complex numbers, okay? Now, okay, so then I can collect terms. I can put the exp sigma t, outside of these parentheses. And then what I will have is, when you have the linear combination of exp j omega t and exp minus j omega t, that is really a linear combination of a sine and cosine. How do I know that? You may remember, this is one of the most amazing things in mathematics. That is called the Euler's identity, right? If you take e to the power j omega t, so you take the exponential of an imaginary number, purely imaginary number, what this is equal to cosine of j omega t. Scratch the j. Sorry for my mistake. So whenever you have this exponential of a purely imaginary number, this can be written as the cosine of omega t plus j times the sine of omega t. Okay? Again, this is something that you should already have seen in some complex analysis or wherever you cover these kind of things. Okay? For me, it's kind of magic, right? The first time I saw this formula is, how is that possible? Okay? But it's actually reality, okay? So this is something that actually connects the exponential, in particular imaginary numbers, to sine and to trigonometric functions. Okay, this is amazing. Okay? But it's a reality, so essentially what you have is that now every time you see exp of j omega t plus exp of minus j omega t, that is actually something that corresponds to a cosine. And whenever you see the difference of exp j omega t minus exp j minus j omega t, this actually corresponds to the sine. Okay, so that's why what happens is that when you have this diagonal matrix with complex conjugate eigenvalues, when you actually go and compute the output, this is actually a function of the sine and cosine of the imaginary part, multiplied by the exponential of the real part. Okay? So you can also write this more compactly and as this form. Okay? And essentially, this is showing that my solution will be given by, okay, some coefficient, some constant multiplies an exponential this is just a normal exponential with the real part of the complex conjugate eigenvalues times the sign of, the imaginary part of the eigenvalues plus some angle. This will be a phase. You can think of this as another coefficient, another constant that depends on initial conditions. Okay? You can either write it as the sum of a sine wave plus a cosine wave, or you can write it as a sine with a phase. Okay? The two things are exactly the same. Okay? Now, again, okay, so this is one of those things where you need to take a leap of faith, right? So now, even though I had these complex eigenvalues, and I have no idea what those complex numbers will be in real life, but so it happens that since you always have complex conjugate eigenvalues, at the end of the day, when you do all calculations, what you get is actually a real function, right? Because, well, I mean, that's what you were hoping for, right? In particular, what does this function look like? We have an exponential. This is e to the power sigma t, okay? That is multiplied by, so this will be the exponential. And this exponential gets multiplied by a sine wave, right? So, and by the way, the sine wave has, what is the period or the frequency of this sine wave? Let's look at the period. This is actually given by 2 pi over omega, right? Okay. So you see that the higher omega, the shorter the period, right? Okay. So you have a sine wave with period 2 pi over omega that is multiplied by an exponential. In this case, it's a decaying exponential, right? So now you see that this is actually an oscillation that decays. Okay, the amplitude of this oscillation decays as e to the power sigma t. Okay? We will look at examples of systems that exhibit this behavior next time, okay? So we're not doing the calculation today. Right, but you may think of, for example, what do you think will happen when, actually if you go back, this is actually something that can describe what happens when you have a pendulum, right, which is hanging like this, okay? And then I give you an initial condition which has some velocity, right? What happens to the pendulum? If I kick it at the beginning, we start oscillating, right? And then eventually the amplitude of this oscillation will decay, and eventually the pendulum will come to rest at the bottom position, okay? And you can see that if you think of this as the angle of the pendulum, this is the evolution of the angle over time. What if I had to, instead of looking at this initial condition response, what I was doing is something more, okay, so now I apply a force, a torque at the joint, right? So now I'm pushing the pendulum to one side. Then I have some, let's say, I give some kind of a torque input, okay? Then what will happen is, what do you think will happen? If I take a pendulum and then push it to one side, will it come to rest at the bottom position? No, right, because I keep giving a torque, right? So it will come to rest at some other position, right? Okay? And the response will look like, remember that the response will contain terms that match the natural response of the system, right? So it will contain terms that look like an exponentially decaying sinusoid. Yeah. Oh, I'm not done yet. So okay, so you have a pendulum, right? But now instead of hanging it, of letting it hang freely, I apply a torque at the joint, okay? So I push it a little bit up, right? And now what do you think will happen? So now we'll oscillate, but probably we'll oscillate about some other equilibrium point, okay? The response will contain, in the same way as before, will contain terms that match the natural dynamics of the pendulum. That is, will contain terms that will be an exponentially decaying sinusoid, plus will be terms that contain the input, right? Which in this case is just a step, just you go from 0 to some value, okay? In particular, as you can imagine, what will happen to a second order system in general is something like that, okay? Okay, so what you will see is that now you have a decaying exponential, right? But you also have an offset that is actually a term that depends on the input. Okay, we look at more at these things, in the remainder of the course. Okay. Okay. Now, what happens when you have, the other case that can happen is now I cannot diagonalize my matrix. Okay. When I cannot diagonalize my matrix, this means that I have some eigenvalues that are repeated, okay? But these eigenvalues actually share the same eigenvector, okay? So this would be eigenvalues that have, in this case, algebraic multiplicity 2, but have geometric multiplicity only 1. Have you done this stuff in linear algebra or anything like that? Ever heard of eigenvalue multiplicity? Okay, some people are admitting to it. Okay. Anyway, so what you need to know is that in some cases, it is not possible to diagonalize the matrix. And the best you can do is reduce it to this Jordan form. Jordan form means that, I always do this, that you have a bunch of repeated eigenvalues on the diagonal, and then you have these numbers above the diagonal, these ones over the diagonal, okay? You can compute these, just do the calculations and compute what the exponential of this matrix will be, and what you will get is that you will have terms that are just the exponentials of lambda, right, or exponential of lambda t, plus you will have some terms that actually contain exponential multiplied by time, multiplied by t, okay? So the, in this case, the homogeneous response is a linear combination of exponentials with that particular eigenvalue, plus terms of the form that exponential multiplied by t. Now, when do these Jordan forms appear in control systems? Typically, the way that, that these things appear is when you have repeated eigenvalues at 0. Okay? So when lambda is 0, then what you will see is, so exp lambda t will be what? When lambda is 0, the exponential of lambda t will be just 1. Okay? So then what will happen is that you will have a linear combination of terms of the form 1, that is some constant, terms of the form t, that is some linear terms, and possibly higher order terms. So you will have formulas, like a response that looks like a constant plus a linear term plus a quadratic term plus a cubic term, so on and so forth. In particular, what you will get is polynomials, okay? So what you're seeing is that in general, the response of a linear system will contain simple exponentials when the eigenvalues are real. So the simple exponential correspond to real eigenvalues. Or you may have this exponentially modulated sinusoid, or the sum of complex conjugate exponentials, okay? And this is when you have complex conjugate eigenvalues, okay? Just to give you an idea, just a little bit like a cheat sheet. These are terms that look like this, okay? So these are just exponentials, okay? These are things that look like this. Okay, so now you have this oscillatory behavior. Or you can have things that look like some exponential multiplied by time. Okay, in particular, when this lambda is 0, what you will have is really polynomials. Okay, so maybe you can have like a parabolic response or a ramp, like a linear response or things like that. Okay. And then, in general, you will have some components of the, so this is time always, right? And then, whatever the input is, you will actually see terms that look like the input transmitted to the output in general, okay? Let me give you an example of a repeated real eigenvalue. This is a simple example of what is called the double integrator, okay? So, yeah.
When did we get the third case? Which case?
Which one? The time-scaled exponentials? This one? Yeah. So this is when you have repeated eigenvalues. So when you have a Jordan form, okay? So if everything is diagonal, then it's only the first two, and of course the input, okay? When you have a Jordan form, then you have these complicated terms that actually are multiplied, are the same as before, but multiplied by time or time squared and so on and so forth. Let's look at an example of a system which has these repeated eigenvalues, okay? And this is actually, one of the simple examples that you can imagine. This is, for example, just a mechanical system where you have m times a is equal to f, right? That's something that you can write as m x double dot is equal to f. This is my differential equation. How do I convert it to the a, b, c, d form? What I will say is that, okay, so let's call x1, x1 dot is equal to x2. Okay, so I will have my vector x, actually, sorry, let me, so this would be the second derivative of the position, okay? I don't want to mix up x, too many x's, okay? So mass times the second derivative of the position will be equal to the force. This is Newton's equation, right? Okay. So then I can choose my vector x to be p and p dot, okay? So what I have is x1 is equal to p, x2 is equal to p dot, right? So then I can write that x1 dot is equal to x2, x2 dot is equal to f. What are my A, B, C, D matrices? So what I want to do is write x1 dot and x2 dot as a function of x1 and xu, and then something multiplies my force, right, my input. So what is the number in here? x1 dot is actually equal to x2, right? So what is the number that multiplies x1 in that equation? 0. What is the number here? 1. What is the number here? 0. Okay. What is the number here? x2 dot is just equal to f, right? So this will be a 0, this will be a 0, and this will be a 1. Okay? So, what is the integral of this? When you were working on, this is physics one, right? And we're looking at the motion of a body with no external forces. Okay, so what is the solution? In that case, you would write that x of t is equal to the initial condition, right? Plus the initial velocity, or I don't know how you wrote it, but maybe something like that, right? So if the force input is 0, then I know that my x of t will be given by my initial position plus my initial velocity that multiplies time, right? I don't know how you call this. This is the formula for the uniform rectilinear motion, right? I don't know how you call that. This is the formula. And you see that, okay, so we got this by, just by simple math. But in a sense, you can also do this as, if you take the exponential of this Jordan, you see that this matrix is in the Jordan form. Eigenvalue 0, eigenvalue 0, and then you have the 1 here. Okay? If you take the exponential, what you will get is terms that just have the form of 1, it's a constant term, and then you have terms that are multiplied by t, and this is the linear term. Okay? So this is a typical example of how these Jordan blocks arise in control systems. Typically, these are due to the fact that you have repeated eigenvalues at 0. Okay? Good. Questions? Okay, now, as we know, as we have seen, the general response is given by some combination, some linear combination of exponentials, real exponentials, or complex conjugate exponentials that are exponentially, or sinusoid with exponentially increasing or decreasing amplitude, okay? And then you may have these terms that are multiplied by t, and then you have terms that match the input, okay? Now, something that is really important, the number one thing that I need to know about my control system is, will this system remain close to equilibrium, maybe deviate a little bit, or will my system blow up and go very far away from equilibrium and kill people in the process and break stuff in the process, okay? So clearly this is the number one question, right? So what we would like to know is, we say that the system is Lyapunov stable if, however, I start from an initial condition that is not at 0, it's not at equilibrium. What I know is that the system will never go too far away from the equilibrium point, okay? May not come back to the equilibrium point, but doesn't stray too far. And in particular, does not explode, does not kill people, and so on and so forth, okay? So Lyapunov stability means that for any bounded initial condition and 0 input, my system, my state will never deviate from the origin, from the equilibrium point by too much, more than some delta, okay? Now, a stronger property is that of asymptotic stability. I say that a system is asymptotically stable if, no matter where I start my initial condition, eventually my system will go back to near the equilibrium, okay? So this is something that's very important, because if a system is asymptotically stable, what it means is that initial conditions do not matter eventually, right? That soon enough, whatever initial conditions, those will disappear, and the effect of the initial condition will be such that it's forgotten and the system goes back to the equilibrium point, okay? Why this is important? This is very important because it allows us to essentially ignore initial conditions when studying the response of control systems. Okay, you know that if the system is asymptotically stable, whatever the initial conditions were, as long as we're still in the linear regime, those will be taken care of, right? So will be forgotten, and the system will converge back to the equilibrium point. Okay? Then I also say that the system is Bibo stable, that is bounded input, bounded output stability, is that if for any bounded input, the system will remain bounded, okay? And then I will say that the system is unstable if it's not stable according to any of these definitions, okay? Now, how do we figure out, just by looking at the model, whether the system is stable, asymptotically stable, Bibo stable, so on and so forth? Remember what the solution looked like. What we know is that the response of a system will be given by, assuming that for now that the system is diagonalizable, okay? So the system will always be, the response will be given by the linear combination of terms of the form x lambda I times t, or forms of, or terms of the form x sigma t times the sine of something, right? Now, the sign of something is something that is always bounded between -1 and 1, so it doesn't really matter, right? So under what condition either these terms or these terms will eventually go to 0, or will remain bounded? as long as the real part of these eigenvalues is not positive, then my system will remain bounded, meaning that it's Lyapunov stable. Okay? You see that? Right? If lambda I is -1, then this would be exp minus t. So that's something that as t becomes large, exp minus t will go to 0. Right? If lambda I is equal to 0, then this exp lambda t will be 1, always equal to 1. So this is something that will not go to 0, but at least does not increase. Right? If lambda I were to be a positive number, say 2, then what I will have here is exp 2t, and this will be an exponential that actually diverges. Right? So if I want my system to be Lyapunov stable, that is never stray too far away from the equilibrium point, then I need the real part of all the eigenvalues to be non-positive. Okay? In particular, if the real part is negative, then the system will actually converge to 0. Okay, so I will say that my system will be asymptotically stable if the real part of all the eigenvalues is actually negative, strictly negative. Okay? Now, if the matrix A is not diagonalizable, then the state output response will also contain terms of this form. Okay, so exponentials multiplied some polynomials. Okay? Now, what happens? So, if the real part of the eigenvalues is actually negative, who wins? The polynomials or the exponentials? No matter what you put in front of it, the exponential beats everything, right? So if the real part of all of your eigenvalues is negative, then you will still go to 0. Okay? What if the real part of your eigenvalues is actually 0? Well, if these eigenvalues are not repeated, that is, if you have no Jordan blocks, then this will be just be a constant, so your system will not be asymptotically stable, but will be Lyapunov stables in the sense that it does not stray away from the equilibrium. However, if you do have a repeated eigenvalue at 0, what happens? Now you not only have the constant term, but now you also have a linear term in t, right? So what will happen is that if you have a system that is not diagonalizable, that is, if you have repeated eigenvalues, okay, in this Jordan form, then in order for it to be Lyapunov stable, you need that all the eigenvalues must have non-positive real part, and there must not be any repeated eigenvalues with 0 real part. Okay. By repeated here, I mean in the geometric sense, okay? So these are eigenvalues that appear in the Jordan form, okay? Also notice that for linear systems, if the system is asymptotically stable, then you can show that it's also Bibo stable in the sense that so will be bounded response for any bounded input, okay? Okay, let's summarize. Okay, let's check. Okay. Do you agree that, any questions on the first point? First point is this message that I said at the beginning, right? So we spent the first hour on it. In order to compute the response of a linear system, what you do is divide and conquer, compute the response to an initial condition, to a non-zero initial condition with 0 input, plus the response to 0 initial condition with non-zero input. Compute those two separately, add them up, that's your solution. We did that for the scalar case, then we looked at how to do it for the matrix case. And we saw that the key point in going to the higher order matrix case is define this matrix exponential. We define it, we constructed it in such a way that has the property that we want, okay? And if we construct the matrix exponential, we can write everything in the same way as the scalar case. And we use the matrix exponential to compute the response of linear systems in general. We gave definitions of stability, and we looked at conditions for stability. Okay? Thank you. I'll see you next week.
two quick questions. I